software. We'll calculate cross-sections for electron-molecule collisions. And what the software does is that it interfaces with two main codes. First of all, MolPro, quantum chemistry package, which provides a variety of information for our codes, including target orbitals and other things. The information that it provides is then fed into the molecular R matrix suite of codes, UK Armstrong Plus, which ultimately calculates the cross-sections. And so the purpose of our software is to provide a user-friendly GUI interface into which the user can enter the pertinent parameters for the calculation. The interface will then run the calculations and repackage the output into a user-friendly format. So the output from the codes is a set of cross-sections and rates for various collisional processes, including elastic scattering and momentum transfer. There are also a range of excitation processes. The electronic, rotational, and vibrational excitation cross-sections can be calculated. There is a method for estimating dissociative electron attachment cross-sections. And there's also a method for calculating the total ionization cross-section. And in the next release of QEC, there will be functionality for calculating dissociative ionization cross-sections using user input of mass spectrum data. So this is the set of cross-sections that the code will provide. So the purpose of this talk is to describe our use of effective core potentials for heavy systems. So why are we actually doing this? Well, there are a set of very important benefits of this. Heavy elements themselves are very important for a number of applications. In particular, of interest to our customer base will be etching and deposition, where heavy elements are extremely useful, and also other applications, fusion, and several others. So the fact that we can develop a capability to calculate cross-sections and provide data for these important processes really represents a very significant step forward in our capability. Previously, this was a limitation really for us. We could only do light-ish elements, molecules containing light-ish elements. Now we have the whole expanse of the periodic table, essentially, in principle, at our disposal, which is a very exciting prospect. However, calculations for heavy elements are demanding. All electron calculations for heavy multi-electron systems are going to be costly because the size of your calculation and the size of the computer that you will require will scale with the number of electrons in your system, so it will quickly become costly. But the solution to this will be to use effective core potentials. So ECPs have two main benefits. They represent up to all closed shell electrons in a functional term that goes into the Hamiltonian. It represents these electrons instead of basis sets. So you shift the demand in your numerical problem away from large basis sets into a simple term in the Hamiltonian, which is just one term, which is already solved. And your basis sets are then left with the lighter demand of handling valence electrons. So it reduces the demands on your calculation. The core potentials are also able to capture relativistic effects, which all electron approaches may not. In particular, relativistic contraction of the valence orbitals will be captured in the valence basis sets that accompany effective core potentials, and this may not be captured in all electron basis sets. So there's a better capture of relativistic effects, so that the overall dual benefit of ECPs is an unusual one. It reduces the runtime of your calculation, but simultaneously improves the physics, which is quite a good pair of benefits to have. So on the whole, this work is very worthwhile. And so how do we actually implement it in QEC? Well, MolPro provides all electron basis sets for all elements up to krypton. Once you get beyond krypton, the default all the basis sets, the all electron part really becomes a basis set for the valence electrons plus an accompanying ECP. You do have ECPs really for all elements. As long as you have a core and electrons outside it, you can use an ECP. You can use an ECP for lithium if you wish, but really it's most useful for elements heavier than krypton. So this previously was our limitation. We couldn't do calculations effectively for molecules that contained anything heavier than krypton. And that will overcome this obstacle. So the ECPs will handle up to all the closed shells in your system, leaving only potentially valence-only electron basis sets to be used. There are a range of ECPs that are available, quasi-relativistic, fully relativistic, and non-relativistic as well. And so the development work that we've been doing in collaboration with a group at Charles University is to, first of all, update the R matrix codes to account for ECPs in the Hamiltonian, and then use the updated codes in the QEC interface. So in the next release of the software, the ECP functionality will be available for use. This is not the first time that ECPs have been used in the QEC software. It was used previously for the ionization cross-section. And the reason for that is that the method we use for ionization only uses data from MolPro. We apply this formula, the binary encounter beta method, and the quantities S, T, and U here are just energies which you get out of MolPro, which use the ECPs. No R matrix calculation is required, and so this could be implemented with ECPs included. The development work here is to extend that capability to the R matrix calculation and therefore to all other cross sections that we want to provide. So just quickly on R matrix theory, this is the general slide that I show on this. The main thing that needs to be taken from this is that in the R matrix method, you're solving an n+1 electron Schrodinger equation for an n electron target and an impacting electron. You have a Hamiltonian and a wave function in these different regions. The work has been to modify the Hamiltonian so as it includes an ECP and modify the wave function so that it can account for valence only electrons, all electrons minus the ones that you've taken care of with the ECP. So ECPs are now included in the multi-electron Hamiltonian within the R matrix method. So how is this actually activated in practice in the software? Well, nothing has changed about the way it's activated. As it was used previously for ionization, that same functionality is used. This is the MolPro setup window that appears in the software if you launch it, where you enter the pertinent parameters for the MolPro calculation. And this is a setup that I've used for SIBR4. And in the advanced options, if you tick advanced options and then tick use an ECP, up will come a list of all the elements in your molecule to which you can apply an ECP. And I've highlighted just bromine here. You can, in principle, use an ECP for silicon as well. I've chosen not to here, but that choice is available. And then that's all the user actually needs to do to use an ECP. So it's as straightforward as possible. So to begin then with the calculations, the first thing I did was a proof of principle calculation, where I calculated cross sections for BR2 and was able to compare an all-electron calculation for the system. You can use an all-electron basis set for bromine if you wish, with an ECP-based calculation. So I was able to run the full 70-electron calculation with a standard basis set, CCP-BTZ, and then compare to a calculation where I used a 28-electron core potential for each bromine atom. Used 28 electrons, that's handling all closed cores in all closed shells in bromine, leaving you just with 7 electrons in the valence shell to handle. So it becomes a 14-electron problem instead of 70. So it is a significant reduction there. And this is the comparison of the elastic scattering cross-section to begin with that we get from the all-electron calculation, this dashed line, and the ECP calculation, solid line. And this really represents excellent agreement in the elastic scattering cross-section across the board. 0 to 15 eV. This is really excellent agreement. Momentum transfer cross-section. Again, this is really excellent agreement between the two methods. There is some slight discrepancy at low energies between methods, although the cross-section is fairly small. But there is reproduction of resonant features in the right place in the all-electron and ECP calculations. So this is really very good agreement. I also calculated excitation cross-sections. These are the excitation cross-sections for the first few excited states of BR2. Again, dashed lines are the all-electron, solid lines are the ECP calculation. And again, everything looks in very good agreement here. The general features, including resonances, are all captured in the same positions, which you sort of expect in the system. So this really represents very good agreement and improves our confidence that things have been implemented correctly. There are higher lying states in this in BR2, but their cross sections really are negligible. As you see, they're falling off towards 0 in magnitude. These are just the first few that actually have a significant cross section. You can also look at the vertical excitation energy that the core produces for each of the states. And in comparison with the all electron and ECP, the vertical excitation energies, again for just the first few states, are in very good agreement. Relative errors are just a few percent across the board here. So all in all, this gives us plenty of confidence in this first test case that things are looking good. I calculated rotational excitation cross sections as well for J equals 0 to J prime transitions. All electron, again, dashed lines need to be solid. Everything looks good here too. So we can be reasonably confident this test case certainly seems to have worked out as well as we could have hoped. So with these results in mind, I then moved on to the next sort of preliminary case that I decided to try again, bromine-based. So SiBr4 was the target that I chose. This is a large system, 154 electrons. And although in principle you can do this all electron, if you do have all electron based sets for bromine and silicon, you don't really want to be doing that. That's extremely heavy. Anything beyond 100, kind of rule out. So although you can do it in principle, the way to go is to use an ECP, and again use a 28 electron core potential for each bromine. That gives you 112 electrons in total handled with ECPs. I've chosen to use an all electron basis set for silicon as well. So this means you're left with a 42 electron problem instead of 154, which is a significant saving. And these are the cross sections that I arrive at. The elastic scattering and momentum transfer cross sections look like this, and these look perfectly reasonable. What I'm really looking for in this initial preliminary case is, do things look at least reasonably physical? Is there anything, I'm just checking to see if there's anything here that looks out of place or unphysical. Really, there isn't. This all looks perfectly physical. There are a set of resonances that are found in both the elastic scattering and momentum transfer. Magnitudes are reasonable. There is some literature data on SiBr4. There are calculations maybe from 25 years ago with perhaps less accurate methods than the R-matrix method. And those calculated cross sections in its energy range of about 80 to 100 square angstroms. So we're in that ballpark. Magnitude looks reasonable. Nothing particularly unreasonable about these resonances either. So this looks good. I calculated the electronic excitation cross sections here. There are quite a few excited states for SiBr4 that come up, but they all have a reasonable profile that you would expect from excitation cross sections. After the excitation energy, things rise up to some sort of maximum, come back down again. That's what they're all doing. They have some resonance structure on top of them. It all looks perfectly reasonable. So this is encouraging. Vibrational excitation, I also calculated for all the vibrational modes for V equals 0 to V equals 1 transition. And again, these look reasonable with some resonance structure. And the code will calculate the vibrational frequencies as well, which is a useful diagnostic because you can compare that with data from NIST. And these are the vibrational mode frequencies that we get out for the various different stretching and deformation modes for SiBr4. The NIST data compared to QC calculation. And again, the relative errors are on the order of a few percent, which is extremely encouraging. It's a useful diagnostic that we use for other cases. So with the results looking promising for SiBr4, I moved on to the next preliminary case, going heavier still, so silicon tetraiodide. This is now a 226 electron system, and to treat this with ECPs, you can use a 46 electron core potential for each iodine. Again, that leaves you 7 electrons in the valence shell to handle. And again, I've chosen the same basis set for silicon as I did for SiBr4. So this problem should now be as tractable as SiBr4. It's still a 42 electron problem. It's basically the same, which is a very handy property. That you can actually, the calculation for this sort of system is really tractable. So these are some of the cross sections I've got out. Elastic scattering. This again looks fairly reasonable. ballpark. Around about 100 square angstroms in the magnitude of the cross section. This seems perfectly reasonable. There's a lot going on in electronic excitation, a lot more in SIBR4. 22 excited states. Now, this in itself imposes quite a demand on the R matrix calculation. Once you get beyond 20 excited states, part of the calculation then becomes quite lengthy and requires a fair amount of memory and that sort of thing. The computation just becomes large. That then puts constraints on the number of electrons as you can have in a system. A large system, lots of excited states, that's pretty demanding. The fact that we've been able to reduce this down to a 42 electron system means that we're able to handle something like this with a lot of excited states. There's a fair amount of structure in here. There probably are things that require further investigation. There's a sharp spike out here beyond 10B and some other structures that aren't quite as smooth as SIBR4. There's maybe a little bit more to look into here. But on the whole, most of the cross sections, again, have the right profile, rising up and falling as you might expect. So you're able to calculate all of these things, which is very encouraging. Again, I calculated the vibrational excitation cross sections with system. Again, it all looks reasonable with some resonance structure there, and the vibrational frequencies again could be compared with data from NIST, various modes. Relative errors, again, a few percent, even for the very low magnitude degenerate deformation, 63 centimeters, just a few percent out. So this all looks very encouraging for these two systems. So then we moved on to tungsten-based systems. So tungsten carbide was a system I took as an initial test case. So for this system, you can take a 60 electron core potential for tungsten. I chose an all-electron basis set for the carbon, so this becomes a 20 electron problem. And calculated the cross sections again. This again looks fairly reasonable. It's a sort of profile you'd expect from an elastic scattering and momentum transfer cross section. Magnitude is somewhat high, but it still looks fairly too unexpected. Here, there's an awful lot going on in electronic excitation. There are a lot of excited states, some of them very low energy, fractions of an EV excitation energy, the first excited state, which is really very low. Again, the cross sections have the typical profile of resonance, top of a rising profile, and some very low vertical excitation energies in there as well. So on the whole, they look reasonable, but there's an awful lot going on. And again, doing this sort of thing with 30 excited target states is really quite demanding. It's a good job that it's a 20 electron system, not an 80 electron system. Rotational excitation, again, came out with reasonable profiles for J equals 0 to J prime transitions. No, particularly unexpected here, so it looks reasonable. Then I really sort of decided to try to push the boat out a bit and do a molecule of interest for deposition, a Febit precursor, tungsten CO6, which is a 158 electron system. Now, this is a different sort of system from the ones I've done previously, where the ECP sort of takes up most of the electrons. Here's a system where you use the core potential for tungsten, you've still got an awful lot going on around it. 12 other atoms and 98 other electrons. So this is a different sort of problem from a numerical standpoint. I wanted to see how the code deals with this sort of thing. So I set it up with just the core potential for tungsten, 60 electrons, all electron basis sets for carbon and oxygen. I could have chosen core potentials for carbon and oxygen as well to reduce it down further, but I chose not to. And here are the preliminary cross sections I get out. Some resonance features occurring in the scattering, in the elastic scattering and momentum transfer cross sections, but nothing that particularly looks physical. This all looks reasonable for starters. Rotational excitation as well. Some deep minima there in the J equals 0 to 3 and J equals 0 to 5 cross sections. but the others look fairly typical. And so this is sort of preliminary cases that I've taken to just to see how the code is performing. So the conclusions on this are that we can now use ECPs in QEC for general polyatomic molecules. Calculations are now feasible. The calculations that I've shown today run on the order of minutes to an hour, maybe 2 hours. So they're perfectly tractable calculations. Further testing is certainly required to investigate some of the features. These are all very new type of molecules. We're maybe not sure what structures we should come up with in some of the cross sections. So I'd say further investigation is required in some of them, but things look perfectly reasonable for starters. It might also be worth investigating relativistic effects in these systems, because you do have non-relativistic potentials as well. And it might be, out of academic interest, it might be interesting to test non-relativistic against quasi or fully relativistic potentials to see what relativistic effects play a role in these systems. And I'd also like to test it for a wider range of systems. I focused on silicon-based molecules, halogens, and tungsten. There's the rest of the periodic table, particularly the middle, that I'd like to take a look at, and probably will do so in the near future. So finally, just to acknowledge my colleagues. So the implementation of ECPs into the R-matrix method was done by the group of Zdeněk Nazin at Charles University in Prague. And then I'd like to thank the team at Quantemol, particularly Oliver Bromley, who is working on the QEC code and also has his own project using ECPs, and the rest of the team. And thank you all for your attention.